So these are some example problems for the moment of inertia, the parallel axis theorem, and then calculating the moment of inertia for various mass distributions. So we're going to look at a solid disk, a rod, and how to calculate a hollow disk as well. So this first one is just the regular moment of inertia. And we're looking at the motion of a 4-meter long bar. So if there's a bar in the middle connecting two masses, and if those masses are each 3 kilograms, we're going to look to see how they rotate around a specific axis. So in our first example, if they're rotating around the center of the rod, then we would calculate the moment of inertia as we have been before. So remember, our moment of inertia equation is I equals the summation of, from some indice I equals 1 to the final one n, that will equal, well, it will be the summation of mi ri squared, where m is for mass, r is for radius or location, and that is what we're going to do for each indice. So since there's two masses, we're going to have two indices. So then our moment of inertia would be equal to the mass of object 1 times the location of object 1 squared. And the reason why we know it is 2 for the radius is because the bar itself is 4 meters long, so therefore half, or the center, would be at 2. So then this distance in here would be that 2 meters, which is going in here for r, plus 3 times 2 squared for the second mass. So we've got mass 1 and mass 2, which then will give us a total of, so 4 times that, so 24 kilogram meters squared. So remember, the moment of inertia has a unit of kilogram meters squared because it is a mass times the radius, or moment arm squared. Now, if it is rotating around one end of the rod, so if instead we have the 3 kilogram mass here, 3 kilogram mass here, and now the distance between them is 4 meters, then what we would do is we would look at the distance, since it's rotating around object 1, you have the mass of object 1, but since it's rotating around this point, we actually say that the distance is 0, because it's rotating around that specific point, plus mass 2 times the new moment arm, so the distance here is now 4 squared, which now will give us a different answer. It will give us an answer of 48 kilograms meters squared. So as you can see, the moment of inertia does change depending on where a mass is located. So that is our first example, just looking at when something rotates around its center versus when it rotates around an end. Now let's look at what's going to happen when we rotate at a point 2 meters beyond the masses. So we still have two masses of 3 kilograms. But now they're rotating around this axis of rotation. Okay, and since they're now rotating around this axis of rotation, we're going to have an additional moment of inertia. So this moment of inertia, again, if we look at our equation, from I equal to 1 to n, we will end up with, for mass 1, this distance is 2. Now this one has a distance, the second mass, mass 2, will now have a distance of 2 meters plus 4 meters, so a total distance of 6 meters squared. So that means that we will now have 2 times 2 is 4, times 3 is 12, plus, we got 6 times 6, which is 36, and then 36 times 3 which is 108, and that gives us a total of 120 kilogram meters squared. So as you see, the further away the axis of rotation gets from the center, the moment of inertia is going to increase. And there is an equation that's going to allow us to calculate the moment of inertia when the system arises, and that is called the parallel axis theorem. So just to recap, the parallel axis theorem, IP, will give us the moment of inertia around a fixed point, and that will equal the moment of inertia around the center of mass plus the total mass times the distance to that new point of rotation squared. So this is our adaptation. So in order for us to figure out, again, the shift when something's rotating around its center of mass to when it's rotating around a new point outside of the center of mass, we would then use this parallel axis theorem. Just as a reminder, this is an equation that is not given to you on the AP exam. This is one that you're going to need to memorize. So again, parallel axis theorem, the moment of inertia around a point will equal the moment of inertia around its center of mass plus the total mass times the distance to the new point of rotation squared. So just to recap about what we've done so far, so if this were to rotate around the center of mass, and we're still using 3 kilograms for our masses, the length of this bar is 4, that means that the distance to the center of mass in here would be 2 meters if the total bar is 4. Since both masses are equal in value, the center of mass would then occur in the middle. So if we're trying to find the moment of inertia about our center of mass, we have 3 times 0. This is our fixed point. And then we'd have 3 times 2 squared, which would then give us a moment of inertia of 12. This means then, if we were to then rotate to a new location, we're going to rotate 4 meters away from our center of mass, that using the parallel axis theorem, we would have our new moment of inertia that we're looking for will equal our rotation of inertia, or our moment of inertia around the center of mass, which was 12, plus the total mass of the system. So since each of these are 3, that's a total mass of 6. The distance from the center of mass to the new point of rotation is 4. So that is why we're going to use 4 squared. And that will give us a value of, so 4 times 4 is 16, times 6, which is our total mass, gives us a value of 96. So now our moment of inertia around this new point is 12 plus 96, or 108 kilogram meters squared. So as you can see, once again, using that parallel axis theorem, the further away our point of rotation gets from the center of mass, the higher that value gets. Now this equation, the summation of mass times the radius or distance squared, works pretty well with what we call point masses, so that's what we've been looking at, like specific points at specific locations. But we're going to need to use calculus for more continuous masses, so like disks, rods, spheres, when that mass is extended over a volume or over an area. So anytime you have a mass distribution like this, instead of setting it up as a summation, we're going to set it up as an integral, where we are going to integrate over r squared with respect to the mass. So we care about where the masses are located. We're going to look at what are called discrete amounts of mass, or dm, and we're going to add them up over a set of limits. So we're going to start off by looking at this for a rod. So what we're going to do first is we're going to look at our rod, and we can agree that this rod will have some length L. That means that this point right here occurs at negative L over 2, because this would be 0. This could happen at positive L over 2. And we're going to call this the center of mass, or so cm, remember capital CM is center of mass, not centimeters. And that will occur at the origin of our system, which is why this will be negative L over 2 and L over 2, which gives us a total length of L. We're going to look at a specific little length dr, and we're going to look at how within this dr there is a tiny dm, a small discrete amount of mass. And the first thing we're going to do is we're going to look at something and we're going to call it lambda. And lambda has to do with this ratio. Sorry about the bell. It's going to be our mass over our length for a system. So that will equal the mass of the rod over its length. And we can call that m over L, total mass, total length. The next thing we're going to do is we're going to set up our integral. So our integral will be from a location of L over 2 to positive L over 2. You're going to have r squared is equal to dm, but we have to make dm be in terms of dr because we want to integrate with respect to dr. So to do that, we can say that dm over dr, that ratio, dm over dr, is going to equal m over L. Therefore, dm is equal to m over L dr. So we actually can then rewrite all of this as I is equal to the integral from negative L over 2 to positive L over 2, r squared, m over L dr. And now we have things all in terms of dr. Now because the mass of the rod and the length of the rod are constant, we can actually pull that out of our integrand. And we have m over L from negative L over 2 to positive L over 2, r squared dr will equal our function. So then we're going to integrate. And so that was step 3, was setting that up in proper terms. Step 4, we integrate. So now we have I equals m over L times r cubed over 3, evaluated from L over 2, negative L over 2, to positive L over 2. And once we plug all of that in, you will come out with a value of ml squared over 12. So I feel like you guys can handle the algebra. Please check that out. Make sure that you get that value.